Okay, everyone, welcome to this week 3 of the problem solving session on the course Control Engineering. This course is taught by Professor Ram Krishna Pasumarthy from IIT Madras, and I'm taking the problem solving sessions every week for the same course. And welcome to this week 3 of this of the session. So again, let's start. So in the last week, you have covered a lot of content. You have covered block diagram reduction, block diagram reduction techniques, and you have covered signal flow graphs, SFGs, and also you have covered the time domain analysis. Time domain analysis of control systems. So, yeah. So let's start one by one. We'll be covering each one of these 3 sections one by one. First, let's start from the block diagram reduction techniques. And I'll not be going into the details of the concepts because I assume that you have gone through the lectures and the slides and you have some basic idea of these concepts. And actually, I'll be briefly revising them, revising important concepts, important terms, important formulas, and then we'll be directly going to the questions. We'll be directly solving the problems so that you'll be able to solve your weekly assignment. So if you consider a closed loop control system, so consider closed loop control system. So a closed loop control system, is represented like this. We have a reference signal. This is our transfer function, open loop. This is our output. Correct. So this is the block diagram of a closed loop control system where my RS is the reference and CS is the output of the system, and GS is the open loop transfer function, right? And we have the summing point here. This is the summing point. Now, if you see, I am feeding the output back to the system, right? So this is the feedback. This term is giving the feedback, or let me represent this P of S, which is a feedback signal, correct? And here, this term here, let's assume this is E of S. It is RS. RS is plus. Here it is minus. So RS minus BS is ES, which is the error term. So this is the block diagram of a closed loop control system. You might have gone through this. I'm just recalling it for so that it will be easier for you to solve problems. Just recapping it. So if you see this BS, what is the value of BS? BS is CS into HS. Correct? This feedback signal, it is HS into CS, correct? Similarly, I told you the value of ES. What is the value of ES? The value of ES is RS minus BS. Now we have to find the closed loop transfer function of the system. So how we will find that? How we will find that? Now we'll find CS. So what is CS? CS is ES into GS. Here you can see CS is ES into GS. Now we have the value of ES. We'll put the value of ES. It implies CS as RS minus PS into GS. Again, you know the value of PS as well. So put the value of PS. So it will be RS minus CS into HS into GS. Correct. So simplifying it a bit, it will be RS into GS minus CS HS GS. So I'll collect the terms of CS on the left hand side. It will be CS 1 plus G of S into H of S is equal to RS into GS. Correct. So, or I can write like this, CS over RS, it's equal to GS over 1 plus GS HS. Or in simple terms, we normally ignore this S. We write it like this, G divided by 1 plus GH. So this is what? It is CLTF. It's the closed loop transfer function, right? So for this system, if we have an open loop, if it was an open loop system, then there would have been no feedback, right? So then the transfer function was GS. But if we close the loop using feedback, then the closed loop transfer function we get is, this is CLTF. So it's a closed loop transfer function we will get as G divided by 1 plus GH. You have to remember this. Wherever you see a block diagram of this type, you have to remember blindly that if it is a negative feedback, here, remember, here it is negative feedback because of this minus term here. So if it is negative feedback, the closed loop transfer function or the net transfer function of the system will be G divided by 1 plus GH. Now, if it was plus here, then it is called positive feedback. And in that case, here will be negative sign. So you have to make sure that as well, that if it is given that you have a closed loop control system with negative feedback, then you know the formula is GS plus 1 plus GSHS. Correct? So one more important thing here. One more important thing. Let me recap here. So if it was GS, then you will give some input RS and get some output CS. So this is an open loop system, right? So this is an open loop system, and for this open loop system, CS over RS, it is GS. But now let's assume you have something like this. This GS, this is HS, this is RS, but you're not closing this loop. You have HS term present, but you're not closing this loop. So in this case, what will be your this is CS. So what will be your CS over RS? It will be GS into edges. It's called loop transfer function. Or sometimes it's called open loop transfer function as well, because uh, it's not uh, feedback is not we are not completing the loop, right? So you will learn we'll shortly cover the rules of block diagram reduction. So you learn that how it comes GS into HS, but yeah, for the time being, you just have to remember wherever you are given, because others have joined late, wherever you see a block diagram like this, make sure that that we can write this simply as the whole term CS over RS. We can simply write it G divided by 1 plus GH. Correct? If it is positive feedback, then negative here. Right? So yeah. So now moving forward, sorry, moving forward, let me, yeah. So, sorry. Okay. So before we begin, yeah, before we begin our questions, uh, just recap some of the rules. You might be knowing them, but again, uh, just for the sake of completeness, I'm just recapping them. For example, if you have a transfer function block G1, which is in cascade with G2, and you are given input X, somebody has not muted. Yeah. So then the output will be, what will the output? Output will be X G1 into G2. Correct? So, or we can write it like this simply. You can replace two blocks with one block, G1, G2, giving X, so that in the output we'll get X, G1 and G2. So whenever you have the blocks connected in cascade, you just multiply them. Similarly, whenever you have blocks connected in parallel, for example, you have G1 and you have G2, you are giving some input X here. So plus minus, plus minus. What will you get? You'll get X plus minus G1 plus minus G2. Again, right? So again, you can replace this whole block as X plus minus G1 plus minus G2. Then again, you'll get X plus minus G1 plus minus G2. The crux is whenever you have parallel blocks, you just add them or subtract them. That's it. Correct? So three things you have to remember. These, as of now, for the question that we'll be doing, I'll be keeping on adding these properties. So as of now, whenever the blocks are in cascade, you just multiply them. Whenever the blocks are in parallel, you just add or subtract them based on the sign in the summing block. And whenever you have a closed loop system like this, blindly remember the transfer function of this will be G divided by 1 plus GH. Now, one more thing. Let's assume this HS is 1. Let's assume this HS is 1. In that case, it will be unity feedback, right? So HS is 1. In that case, we call it unity feedback. And when it is negative sign, when it's negative feedback, then what we call it? Negative unity feedback. In that case, we'll get G divided by 1 plus G, is H is 1. Okay. So now let's start solving the questions. So question number 1 is on your screen. We try to solve it, right? So at first it looks difficult, but when you analyze with the rules I told you right now, it will be easier. So if you identify this block and this block, they're connected in feedback. They're connected in negative feedback, right? So for this block, what we can write, can we write the net transfer function for that block is G1 divided by 1 plus G1, G2, right? Right? Can we write like that? Similarly, for this block, what can we write? For this block, we can directly write G4 divided by 1 plus G4, G5, because I told you they are in feedback, so we can directly write like that. So then we can reduce this block diagram. We can reduce this block diagram a bit like this. So let's assume I replace this with x1 and this with x2. So what will I get? I have this R, then I have block x1, then I have G3, correct? Then I have x2, then I have G6, correct? Then I have a summer here, which is positive, positive, and positive. Here it's Y, C. Oh, sorry, it's Y here. Right, so similarly from here, I have G8 going here, and on this side, I have G7. So now you can clearly see this is in cascade now. All these, this X1, G3, X2, G6, they all are in cascade now. I right now told you whenever these blocks are in cascade, just multiply them, right? So what will be our net transfer function? It will be something like this. We have R, and let's assume this whole cascade, this X1, G3, X2, and G6 is equal to X. In that case, what will be our block diagram? A reduced block diagram will be, this is R, this is G7, this is X, this is G8, plus, this is Y. Now, again, they are in parallel. So when blocks are in parallel, they get either added or subtracted. So here we have summer block, which is only like adding the signals. So what we will get, Y over R, the net transfer function will be G7 plus G8 plus X. Or when we put the values, it will be G7 plus G8 plus G1, G3, G4, G6 over 1 plus G1, G2 into 1 plus G4, G5. So this is the required answer, right? So initially, it felt a bit harder, but as we try to visualize it more, so it was easier. Only two feedback loops, then cascade, and then the parallel connections. So eventually it becomes easier. Correct? Now on the same grounds, can you solve this problem? Very simple. Slightly, I will increase the difficulty of the problems. So can anyone try and find the answer of this problem. Make sure you take care of these signs. On the above, it's minus. On the below, it's plus. Or I can simplify it for you. This is R. So can we write it like this? Can we write it like this? Okay, previous answer. Previous answer is this. Somebody is asking, can you please show the previous answer? So previous answer is like this. And then this is the question. See, we have 3 blocks here. And I simplified it a bit for you guys. And we got this block. Now, can you, now it's very easier from here. What's the next step? Next step is very simple. It's a feedback. So if it is feedback, then C over R, it will be G divided by 1 plus G into H minus F, which is equal to G divided by 1 plus GH minus GF. Does it make sense? Is it right? Okay. Anybody has any question? Right. So if you have understood now, if you have understood this question, then you should be able to solve this question. Okay. You know, it's obvious. The direction is like this. This is arrow. I'm giving arrow here. What are you saying? You're saying what is the direction of F and H to summing point? Yeah, the direction was like this. It's like this. How H minus F came. Now can you see? See, H is, I just wrote, these are in cascade. Sorry, these are in parallel. H and F are parallel. F is positive and H is negative. I wrote it in negative feedback way such that, so that we can apply the negative feedback principle. So I wrote it like H minus F. You see, H is negative, so it's negative feedback, but F is positive. So see, H is negative here. This is the negative sign. And F is positive. So minus into minus, it becomes positive. So that's why F is positive here. Anyway, so now it will be clearer as we proceed. So now, can you solve this question? Again, very simple. Very simple. You just have to identify summing blocks. Like, sorry, you just have to identify the cascade, the parallel connections, feedback, whether it's positive feedback, negative feedback, you just have to identify that. Can anybody
Answer is
solve?
this loop is reduced by the standard gain formula.
Yes, yes. Can
G1
you tell the
upon
final answer?
1 plus G1 H1 into G2 upon 1 plus G2 H2.
Correct. So it's very simple. What you have to do, see, See, if you identify this, let's assume it's T1, transfer function of block 1. What is this? It's G1 over 1 plus G1 H1. Similarly, if you identify this, it is G2 over 1 plus G2 H2. So we get these two blocks, and these two blocks are in cascade. So if they are in cascade, you just multiply them. So our net transfer function, which is CS over RS, what it will be? It will be T1 into T2, which is G1 G2 divided by 1 plus G1 H1 into 1 plus G2 H2. Correct? Right? Does that make sense? Is it clear to everyone? I'll be keeping on increasing the difficulty level. Should we move forward? Has everybody written this? I'm giving some time because the questions are already written and for you guys to note these questions. So don't write in the chat box if you want to give answers or just like the previous member just unmuted himself and answered the question. Why are you writing in the chat box? Because I'm not able to see the chats all the time. So you should better unmute yourself and answer. Don't worry whether the answer is correct or not. See, it's difficult to write in the chat as well. So again, now let's move forward to the other question. Now try to identify what you can do. Like, are there any, again, the arrows are like this, right? So again, identify whether there is any positive feedback, negative feedback, or cascading, or parallel connections, and accordingly you solve the question.
Sorry, G2 and H1 they are in parallel. They can be added.
Uh, yes, they're actually, if you clearly see they're in positive feedback. They're not in parallel, that's feedback. This is G2, the output from G2 is YS, and I'm giving that signal back. Like if you,
Yes.
with
So
this
it
signal.
is a G2 upon 1 minus H1 G2.
Yes, yes. For positive feedback, it will be minus. So I'm simplifying it a bit for you. So it will be, let's say if it's T1, it will be G2 over 1 minus G2H1. That's positive feedback. Then the other block will be in cascade with this T1, which is in negative feedback with H2. I think you should be able to solve the problem. So this T1, it will be in cascade with this G1. It will be, the block diagram will be reduced like this. T1, G1, and H2. Does it make sense? Right? So then you should be able to solve it. What will be? What will be the net transfer function? Ys over xs. It will be T1 G1 divided by 1 plus T1 G1 H2. Right? Then when you put on the values, what you get? The final value will be something like this. Please match everyone. G1, G2 divided by 1 minus G2H1 plus G1, G2, H2. Is everybody getting the same answer? This is the final answer. If there is any doubt, please let me know. Please unmute yourself and let me know.
Yes, sir. We have got the same answer.
Thank you for confirming. So if everybody has solved this question, just giving 1 minute for everyone to write, everyone to solve. In the meantime, I'm giving others this question. Please try to solve this question now. Very simple again. Find the overall transfer function of the block I'm giving some hints. So we have G here, 10 over S into S plus 1, and H here, S. So we have G and S, and we have a negative feedback, this part. So we can write, let's assume that is T1. What will be T1? It will be G divided by 1 plus GH. So G is plus 1 divided by 1 plus 10 divided by S into S plus 1 into S. Correct? So what will you get? You will get 10 over S into S plus 1.
So
Now,
last answer is, I have got last answer.
yeah, what is the last answer?
10 upon S square plus 11S plus 10.
Great. So then when we have solved this loop, this unity feedback, then we got this T1. This T1 is then in negative feedback, negative but unity feedback. Then H will be 1. So then T1 and H1, then finally when we solve it, we'll get, or let's solve for others. Finally, we'll get T as 10 divided by S into S plus 1, all divided by 1 plus 10 divided by S into S plus 1. Right? So here it's 1, and finally we'll get the answer as 10 divided by S square plus 11S plus 10. So I hope everybody is able to understand. So you have to be very careful. You have to see where is, or sometimes it's not possible for you to figure out whether there is actually some unity feedback or not, or whether there are any cascading, or whether there are any summing blocks, this parallel blocks. But if there are not any, we have to create the possibility by moving the summing blocks, or by moving the takeoff points, right? For example, if you consider this thing, let's assume I have I have this summer. I have a summer and block G1. So I'm giving X1 as input and X2 as input. Then what should I get? I should get G1 X1 plus minus X2. Correct? So you have actually learned these concepts. I'm just recalling. But what if I want to transfer because of some reasons? Because I'm not able to get any unity feedback, I'm not able to get any closed loop system or any summer block or any cascading, which will make my things easier. So, but if I'm able to move this summer in front of this block, then it will be my calculations will be easier. So if I have to move this summer block in front of the block G1, so I'll do that. This is now X1, then G1 here, and summer block I have moved to in front of G1. But output should be same. Output has to be the same whatever I had earlier. So in that case, it's X1 into G1. So here I will get X1 G1. And then the output, in order for the output to remain same, I'm just multiplying the block gain G1 with the signal X2, right? So that I get the same output. So whenever you just have to remember, whenever you are moving a summer block in front of a uh, block, in front of a gain, or in front of a block G1, you have to make sure the output remains unchanged. So either you check yourself or just remember that whenever summer block comes in front of a block, you just have to multiply the signal with the gain of that block. Similarly, similarly here, I just want to move this summer block before the gain block G1, right? So the output is X into G1. So here it will be X into G1 and plus minus X2. So X1 into G1 plus minus G2 here also X1 plus minus X2. Now, if I want to transfer the summer block before the G1 block, I have to make sure I again get the same output, right? So I have just moved this summer block before the gain block G1. Then if we see, in order for us to get the same output, I have to divide by the gain of the block G1, right? Then and only I can get the output same as that of the previous thing, right? So whenever you are moving a block, gain block after, whenever you are moving a summer after the block, just multiply that. And if you are just transferring that before the block, just divide with the gain of the block. Similarly, let's assume you have a takeoff point. So this is a takeoff point that you are having. So this is X. So I'm taking the signal X from here. That's why it's called takeoff. So I'm taking off this signal from this. So this is my takeoff point. But now if I want to shift this takeoff point to this side, my output should be the same. So see, now my takeoff point X, it should be X only. So if it is, I have shifted it after the gain block G1, then if you see, I have divided with the gain of the block G1. It's just opposite of the summer block, right? It's actually common sense. You need not remember this. You just have to make sure that your output remains the same. So whenever you are when you are transferring this takeoff point in front of the block, just divide with the gain. So why I'm saying just remember it, because when you have a complicated transfer function, it will be very difficult to check the output, right? Similarly, if you have a takeoff point here, this is the takeoff point. I want to transfer it before the block G1. What I have to do, I have to multiply with the gain of that block to the signal, correct? So opposite to that of summer block. I hope this is clear. So if this is clear, then please note down this question. Please note down this question and try to figure out what you can do. What you can do, uh, because there are no visible feedback loops.
So we have to shift this pickup point here up H1
It's
after
it's you
G2,
have to
G3.
think, because you have to think in such a way so that you get things easier. So how you will get things easier? First of all, if you get any feedback loop, then you know how to deal with feedback loop. Secondly, if you get things in cascade or parallel, yeah, then again you know how to solve. So there can be multiple ways. So can you come up with a way? Uh, it
So
it actually
G2,
comes with practice. Yeah.
yes, sir.
Yes. Yes.
G2,
Yeah.
G3, and this S2, this is actually the feedback loop, but we have to take this
Yeah.
pickup point after this block G3.
So you mean this point?
Yes, yes.
So if we shift, okay, let's try. Like if we shift this takeoff point here uh, uh, after this block G3, I told whenever we have to shift, whenever we have to shift the takeoff point before the gain block, we have to divide with that gain. Correct? So here, if we are shifting this point, let's assume this is our takeoff point. If we are shifting this way, then what should we get? So I'm just rewriting it, just remaking it. So like this, wait, right? So I'm just remaking it. So so I said I just shifted this takeoff point to this point, and now this was initially H1. Now what will be the value of this thing? There will
H1
be
by
another
G3.
gain block 1 over G3. So I'll directly write G3 here. Is this clear to everybody? Why I wrote this directly? Because I moved my takeoff point from this place to this. Then I know when I have to move my takeoff point in front of a block, then I need to divide with the gain of that block. So that's what I did. Now can you see? Now can you see? There is one catch now. Now if you see this thing, can you figure out what's that? So is it in this is the feedback loop, right? So if the transfer function of this block is T1, can I write, and these are in cascade. So can I write G2 G3 divided by 1 plus G2 G3 into H2? Can I write like this? Anybody has any problem with this? G2 G3 divided by 1 plus G2 G3, because these two blocks are in cascade, so I can write replace them with one block G2 G3. Now this block is in loop with in feedback with this H2, so I could write this T1. Now this T1, if we see this T1 is in cascade with G1, so I can get my reduced order block diagram something like this. G1, T1, this is C of S. Here, this is H1 over G3, right? So now again, these are in cascade. So my final, it will be plus minus T1 G1, this is C of S H1 over G3. Is it clear, everybody? Then finally, this T1 G1, this is also in feedback with H1 G3. So if you solve it, you will get C of S over R of S as G1, G2, G3 divided by 1 plus G2, G3, H2 plus G1, G2, H1. Is everybody getting the answer? Is everyone getting the same answer? Should we move forward?
Yes, sir.
Right. So now let's solve one last question from this block diagram reduction techniques. So can you solve this question? So this is figure A. This is figure B. The question says the block diagrams shown in figures A and B are equivalent. So for what values of X, the block diagrams A shown in figure A and B, they are equivalent. Again, this is a very good question. So it's from your assignment, practice assignment. So options are also given. So please come up with the answers. You should be able to solve this question now. Okay, Ramya has said E. Okay. Can you please unmute yourself and explain it a bit for others that how you got the answer as E? Ramya, can you please unmute yourself? My speaker is not working. Okay. Okay, no problem. So I'll just solve it for others. Anyone else? Anyone else has got the answer? E? Okay, let's solve it. So let's look into this diagram. We have X and 1 divided
Please show
by,
the options. Options.
okay, options 1, 2, S plus 1, S plus 2, and 2S plus 3. Okay, let's solve it for others. So this X and the block 1 divided by S plus 1, they are in cascade, right? So we can write, we can replace that block with S, X divided by S plus 1. Correct? So my CS over RS, what it will be, I replace this feedback, sorry, this blocks and cascade by this, then don't confuse that it's negative feedback. There is no negative feedback. Actually, we are giving this R signal again. to a summer block. So here the signal will be x divided by s plus 1, and from here we are getting this r as -1. It's minus, right? So we can write this as uh, -1, right? So -1 and this, then if you simplify it, you'll get x minus s minus 1 divided by s plus 1. And then if you compare it with figure 1 options, that is s plus 2 divided by s plus 1, so I'll get, sorry, I should get, it implies s plus 2 is equal to x minus s minus 1. It implies x is equal to s plus 3. Correct? So I hope now you'll be able to solve these problems from block diagram reduction. But again, this is a very tedious task. You cannot all the time look into these blocks and then solve it, because then multiple times you have to redraw the blocks. So there is another approach. Of solving these transfer functions that is called as signal flow graphs, right? So now we will see how we can solve these block diagrams or these complex block diagrams using signal flow graphs. Again, you would have gone through the contents and the lectures of the last week, so I'm not going into the detail, but again, just revising the formulas. So one important formula is Mason's gain formula, and this is the formula that's used to find the overall transfer function of a block, right, of a system. So this is Mason's gain formula. It's the whole transfer function, the overall transfer function, or the gain, that is equal to summation pk into delta k over delta, where pk is the gain of the kth forward path, right? And delta, it is given by this formula 1 minus sum of all loop gains, then plus sum of gains of product of two non-touching loops. Means we have to take the sum of products of at least two non-touching loops, gains of two non-touching loops, then subtract sum of gain of product of three non-touching loops, then again plus sum of gains of product of four non-touching loops, and so on, right? So this formula will keep on increasing. The terms will keep on adding. And this delta k, it will be the value of delta excluding the loops that are touched by forward path pk. I know either you already know this formula and it's not that clear as of now, but I'll try to explain you with the help of this example that how we can apply this Mason's gain formula to solve these signal flow graphs. And accordingly, actually, this signal flow graph, it has come from a block diagram, right? So we have simplified that, and now we are able to write that block diagram in terms of this signal flow graph. And we will be solving this signal flow graph now in order to find the overall transfer function of the system, which was again, that task was that we were solving the same thing using block diagrams, right? So now, in order for us to apply Mason's gain formula, we have to identify, first of all, see, there are two things. One is this forward path, right? PK, then delta K associated with forward path and delta, correct? So forward path we'll understand first. Then what are these loop gains and what are non-touching loops? Uh, quickly, I'll try to like brief it. So the starting point is A. In the question, the starting point is A and the end point is F. So if you want to go from this A to F, like what are the different type of routes you can follow to reach to this point F. One route is straight, this, right? We can go from A to B, B to C, C to D, D to E, and E to F, correct? And the other one is like this. You can go from A to B, B to E, and E to F, correct? So I'm just deleting it. So there are two parallel paths, correct? Sorry, forward paths. So we identified what are forward paths. In order for us to go from our input, our starting point to the end point, what are the different ways, what are the different routes to go, right? So my first forward path, P1, there are only two ways. There are only two paths available. There is none other path so that we can reach from A to B. So my P1 is like this. Let's say my P1 is like this. It will be 1, A to B, it's 1, and B to E, it's 5. So I multiply them because they are in cascade. And from E to F, it's again 1, right? So 1 into 5 into 1, it is 5, correct? So what was the name of this forward path? It was A, B, E, and F. So we started from A and reached F using this forward path, and the value of P1 is F. And if we see the Mason's gain formula for this graph, it will be like this. The overall transfer function, it should be P1 delta 1 plus P2 delta 2 over delta. Correct? Why it will be only P1 and P2? Because there are only two forward paths. So we will be only having P1 and P2. And with P1 and P2, we will be having corresponding deltas, delta 1 and delta 2, and one delta in the denominator. So we will be trying to figure out these things, like how we can get this. So we got P1. Now we should go look for P2. So what is P2? P2 is A to B, B to C, C to D, D to E, and E to F. So it is 1 into 2 into 3 into 4, which is equal to 24. And it's what? A to B to C, D, E, and F. Correct? Correct. So these are the corresponding gains. This one, A to B, its gain is 1, B to C, gain is 2, C to D, gain is 3. You just have to be very careful. Right? So we are done. With P1 and P2, we are done. Now, we have to find first delta. Then from delta, we'll find delta 1 and delta 2. So what is the formula for delta? The formula for delta is 1 minus sum of all loop gains. So first we'll see what are loops and what are the loop gains. Then we have to see sum of gains of product of two non-touching loops. Correct? So first we will see what are loops. So loops. So from this figure, if you start from a point and then again, so see, this is loop 1. This B to C, C to B again, right? So loop number 1 is B, C, B. What is the gain? Gain is 2 into minus 1. See, B to C is 2 and C to B is minus 1. So B, C, B, the gain is minus 2. What is loop number 2? So this was loop number 1. Let me write it as L1 equal to this, then L2. L2 is, again, here, C to D, D to C. So C, D, and C. It will be 3 into minus 1. It will be minus 3. Similarly, we have L3. L3 will be D, E, and D. So D, E, and D, we have 4 into minus 1, it's minus 4. 4 into minus 1, it's minus 4. Now, do we have any other loop? Do we have any other loop? What's a loop? You start from a point and you have to reach back to the same point without touching any node. Any other? So if you see this thing, B to E, then E to D to C to B. So again, you are able to come back to B. So there is another loop. There is another loop for which is B, E, D, C, B, and the value is -5. Sorry, it's 5 into -1, -1, -1. So it will be -5. You see this? So from B to E, it's 5, then -1, -1, and -1. So it's 5. So in total, we have 4 loops. So if we find delta, what will be delta? Delta is 1 minus sum of loop gains. What is loop gains? -2, -3, -4, and -5, right? Now plus. Now what's another thing? We have to sum the gains of product of two non-touching loops. Now we have to identify, are there any non-touching loops, right? See, this loop, B, B, C, B, it touches this another loop, C, D, and C. So they are not non-touching, but this B, C, and B with D, E, and D, they are non-touching. They don't touch each other. So there is a pair of non-touching loops. And what's their gain? Their gain is 2 into -1, -2. So we have this L1 and L3. L1 and L3 are non-touching loops, and their gains is -2 and -4. We have to write their product and sum them up if there is any other. So there is none other than this loop, which is non-touching. So we can write plus the product of gains of two non-touching loops. So L1 and L3, it will be -2 and -4, right? Then minus. Are there any three non-touching loops? No, there are no three non-touching loops. Stop here. I'll stop here, right? So wait a while. Right, so my delta is 1 minus minus plus 8, 14, so wait, plus 8. So which is equal to 23, correct? So this delta is equal to 23. So from this formula, we have found P1, we have found P2, we have found delta. Now what else do we need? We need delta 1 and delta 2. Now see from the graph. Again, the formula for delta 1 and delta 2 has to be the same as that of delta, but this will change. Like see here. So if we consider path number 1, which is A, B, E, F, so this path, we have to see what are non-touching loops. We have to exclude. So delta is delta k. So delta 1 is the value of delta excluding loops touched by pk. So here delta 1 will be delta, but we have to exclude the loops touched by p1. So what are the loops? They are touched by p1. So this loop goes away because it's touched by p1 here at p, and this loop again, it goes away. It's touched by p1 at e. So only loop that remains is this middle loop, correct? So we have the value of delta 1 as 1 minus only the gain of middle loop. What is the gain of middle loop? It's 3 into -1. It's -3. It's -3. Now plus. Now, are there any loops, any two non-touching loops? Again, with respect to P1, there are no, because only this one loop was left, and there are not two loops. So we cannot go beyond one, right? So we just stop here. So our delta 1 will be 4. Correct? So our delta 1 is 4. Now let's move to delta 2. Delta 2 is 1 minus the transfer function now of this block. Sorry, now this path, we have straight path. It's touching this loop at this point, touching this loop also, touching this loop also, touching the bigger loop also. So there are no loops. So my delta 2 will be 1 minus 0. It will be 1. The overall gain, the overall transfer function from the Mason's gain formula, P1 delta 1 plus P2 delta 2 over delta. What it will be? P1 is, what is P1? P1 is 5, delta 1 is 4, plus P2 is 24, and delta 1 is 1. P2 is 24, yeah. And delta 2 is 1 divided by the delta is 23. The overall transfer function of the block or the gain, it's coming out to be 44 by 23. Right? Anyone has any doubt? I'll just recap. Just recap. So this is Mason's gain formula. It's used to find the transfer function of a system from its signal flow graphs, the overall transfer function. So it's given by sigma summation of pk delta k over delta, right? So it will be, if there are two forward paths, it will be P1 delta 1 plus P2 delta 2 over delta. If there are three forward paths, it will be P1 delta 1 plus P2 delta 2 plus P3 delta 3 over delta. Now we have to find this P1, P2, P3, so on, and we have to find delta. Then when we find this delta, from delta we can find delta 1 and delta 2 and so on by excluding the loops which are touched by the corresponding forward path. Right. And when we are done with that, applying this formula, we will be easily able to find the overall transfer function of the system. Correct? Now, if you have understood this, can you solve question number 2? Can you solve
Sir,
question number 2?
sir, is it sum or is it product?
No, it's sum.
No,
Which one?
in delta you wrote 1 minus sum of
Uh-huh.
gains of product. What does that mean?
Ha. Yes.
Is
So
it
it is
sum or
sum of products. Sum of products. You can remember like this. For example, here. When we consider this forward path P1, which is A, B, and E, we got uh, two loops. Uh, Sorry, wait. You were saying delta. Delta is delta is 1 minus sum. Okay, delta is 1 minus sum of all loop gains. So loop gains is okay. Then sum of gain of product of two non-touching loops. Okay, yeah. So it means there are two non-touching loops. This loop 1 and loop 2. Let's assume this is loop 2. So they are non-touching loops. So we have to take the product of gains of these loops and sum them up. How sum them up? For example, we take the product. The product is 2 minus minus 2 into minus 4. Now, if there would have been more number of non-touching loops, then we would have written plus, then the gain of other one. Let's assume that's minus 1 into minus 4 plus something, something, something. You got it? So it's
yes, sir.
actually the sum of products.
And
Sum of
one
products.
more thing, in the loop 4,
Uh,
uh, you told uh, the loop is nothing but where node will not come. But you are taking the node in the loop
no,
4.
we are not touching them. We are like, see, from here we are not stopping at node.
But it is touching, right? In C to D, it is touching. D to C,
Uh, yes, you mean to say this thing, E to D.
yes. Loop 4,
Yeah,
loop.
precisely. I should correct. Node is like, sorry, loop is you have to start. Yeah, you have to start from a node and you have to come back, but you don't have to uh, like take that you don't have to count any node twice. I think that's the correct number. Still, I'll have to check it. What's the definition? But I hope uh, there is no doubt in terms of the solution. So loop we can check. What's the definition of loop? We have to wait 1 second. Yeah. So we start from a node. If we do not count that twice, then that is loop, I think. Or maybe I can check what's loop. Yeah. So the definition of loop is it's a path that originates and terminates at the same node and along which no other node is traversed more than once. Is it clear? It's a path that originates and terminates at the same point, but along which no other node is traversed more than once. Does that make sense now? I hope now there is no question,
Yes,
no
yes.
doubt with respect to that. Yeah, thank you. So with that, if are you able to solve this question using Mason's gain formula? Again, I told that I'm not able to check the charts all the time. So better unmute and ask. Don't be shy, because uh, then it will be more interactive and we can come at like good conclusions. So if you see here, so there is only one forward path, right? So let's assume that is this P1. So there is only one forward path, which is P1, and the gain of which is 5. So what should be Mason's gain formula? Mason's gain formula should be P1 delta 1 over delta, right? So we know P1. Now we'll find delta. What is delta? Delta is 1 minus sum of all loop gains. Are there any loops? Yes, there is one loop, the gain of which is 0.5. So 1 minus 0.5. There are there are not more than one loops. So no two non-touching loops, no three non-touching loops, nothing. So the value of delta is 0.5. Now the value of delta 1 is 1 minus, again, it's the value of delta when you traverse P1, and we have to exclude the loops of P1. Right, so again, the loop, it will not be counted because it's already touching P1. So my delta 1 will be 1. Then it implies my overall transfer function. Sorry, it's actually x2 over x1. Here, x2 over x1. It's equal to P1. P1 is 5. Delta 1 is 1 over delta, that is 0.5, which is equal to 10. Correct? And we are asked, if so x2 over x1 is 10, it's given that x2 is p times x1. So from here, we can see x2 is 10 times x1. So the value of t is 10. Is that clear? Or is there any other question? I'm sorry for the sound in the background. Cannot avoid it. So now can you solve this question? I'll give you one hint. There are many rules which you have already gone through. I'm assuming that you know those rules and regulation, like for these signal flow graphs. But again, revising uh, just for you guys, and that is at the input, on the input side, self loop is invalid. So self loop at input is invalid. That is, it's not considered. So this is input. Then we have G. Then we have output, right? So maybe this is X. This is Y. And on the input, we have a loop H1, a loop with again minus H1, which is actually invalid. So in questions, you'll be given in exams, you'll be given such questions where you'll blindly apply Mason's gain formula and end up with wrong answers because the self loops at the input is invalid. So you don't have to consider. So then what is your P1, parallel path 1, that is G. Then it becomes the same question as it was earlier, right? So then again, delta, it will be 1 minus H2, where 1 plus H2 and delta 1 is 1. Then transfer function, that is y over x is equal to G into 1 divided by 1 plus H2. So the catch was the input loop, the self loop at the input is invalid. You don't have to consider that. Now, can you solve this question? This is a very, very interesting question. So if you are able to solve this, then you have
In previous
understood.
question, loop gain
Yeah.
is negative, H2.
Yeah. Which one? H2 is negative.
Okay.
It's negative here. So now you should be able to solve this question. It's a very, very interesting question. Clearly identify the forward paths. Can you tell me, can anyone tell me how many forward paths are there? Yeah, can anyone tell me how many forward paths are there?
One forward path.
Yeah, there is only one forward path. You just don't have to get confused because CS is here and RS is here. There is only one forward path. That's it. So here we have only one forward path, P1, which is equal to 1, which is equal to A, B, and C, right? So then what will be the Mason's gain formula? That will be transfer function is equal to P1 delta 1 over delta. So it's a bit easier for us because we only need to calculate delta and then delta 1, right? So for delta, there are many loops here. We need to first identify loop gains, then we will go for non-touching loops, and then so on, right? So
Sir,
let's
this path
identify the
gain of
loops.
P1 is,
One, sorry?
acha, path gain of ABC.
A to B is 1, B to C is also 1. It's given. This.
Acha, this is only forward path. We are not coming like this.
Like what?
Means
A2?
A to B to D to E to F, then F to D.
No,
So it will
like,
not be forward path. Okay, okay, sir.
no, yeah. So P1 delta 1 over delta. So let's, for delta, let's look for the loops. So this loop number 1, it is B, D, and B. What is BdB? That is minus 2 over S. 1 over S into minus 2, that's minus 2 over S. Similarly, we have L2. L2 is E, F, E. See, E, F, this is E, F, and E. It will be minus 3 over S. Similarly, we have L3, D, E, F, D. So see, D, E, D, E, F, and D. So that is minus 24 over S, because this is 6 into 4. So yeah, so we have these three uh, loops. Then we can write delta. What will be delta? Delta will be 1 minus sum of loop gains. That is minus 2 over S, minus 3 over S, minus 24 over S. I hope this background noise is not more. This is there is this college fest going on. Sadly, the fest arena is just beside our lab. Sorry for that inconvenience. Now, plus we have to look for sum of products of two non-touching loops. Now we can see L1 is B, D, and B, and L2 is E, F, and E. Clearly, they are non-touching loops, right? So we can write sum of two non-touching loops. That will be 6 over S square. Sum of products of two. It's this 3 into 2, 6 minus plus over S square. Correct? So there are not any three non-touching loops. So I'll stop here. And my delta will be 1 plus 29 over S plus 6 over S square. Then when I go for delta 1, I told you it is delta without taking into consideration the
I have
loops.
one doubt, sir.
Sorry?
I have doubt how this 6 by S square has come.
Yeah. So if you see, this is from the formula of delta. Delta is 1 minus sum of loop gains plus sum of products of loop gains. So non-touching, sum of products of gains of two non-touching loops. See, so here we have this loop BD and B, and we have this loop E, F, and E.
Yes.
This loop. So they are non-touching. So the gain
Yes,
is 2 over S. So for loop 1, it is 2 over S. And for loop this 3 or loop 2, it is 3 over S. So I have to take product of them, because here, if you see in the formula, I have to take product. So product is, sum of product of 2. So product is minus 2 over 3 over S into minus 3 over S. That will be that will be 6 over S square. So is it clear now? 6 over S square.
Yes.
Now we have to see delta 1. How we have to take find delta 1. So we have to ignore those loops which touch this forward path B1. So clearly we can say only this loop B and D, it touches this forward path. So we'll not consider this, but we will consider the other two. So it will be delta 1 will be 1 minus 3 over S minus 24 over S, which is equal to 1 plus 27 over S. And the final transfer function, it will be nothing. Just apply these values here. The final answer will be, I'll just write answer, will be S into S plus 27 divided by S square plus 29S plus 6. So you'll have to practice because these two topics, block diagram reduction and signal flow graphs, they become clear by practicing more and more. So moving forward, because we haven't
Sir,
solved.
sir, why are you considering the other loop B, C, D, E?
Sorry, B, C, D, E.
Yeah,
Can-
only ABC is the loop. This one. Why are you
ABC is the
considering?
loop, right?
Yes. Why are you considering
Why
B, D, E, F?
B, D, E, F? Why am I considering B, D? Why not B, D, E, F?
There is no input there. Only it is touching the output. Why are you considering it?
Which one? Which one? B, D, B.
B, D, E, F. All the loops. There are no
Where I
loops
have considered? Where I have considered B, D, E, F?
in the loop. In the loop L1, L2, L3, and
So B, I have considered B, D, B. See, B, D, and B. This is the loop. B, D,
no.
and B.
No, it should be like
Yes.
if there is input and output between that only if there is any loop, then only we should consider.
No. When did I say that? It should be between input and output. That is the path. That's the path. Forward path.
Even
That's between
even
input
if
and
it's
output.
coming from other point, also we should consider.
Like I'm not able to understand.
If it is
What are you
coming
saying?
from other point to the C,
If it is coming from the other points of C,
other
sorry.
path means F, E, D, B to C.
Uh-huh. F, E, D, P.
It is
Can
not
you
coming
again be
from.
more clear?
Yeah, it is not coming from A, B, C. It is coming from F,
Which
E,
one?
D, B. The
Which one?
loops. The
All
loops.
three loops?
Yes.
Yes, they are not coming from forward path. That's why I've not ignored them. I have not ignored them in this delta one. See, I've not ignored them. 3 by S, that is not see here. I said when we have to calculate delta one, we have to ignore we have to calculate it from delta by ignoring those loops which are touched by the forward path P. So here there is only one forward path, right? So, and this forward part touches this loop L1. Let's assume this is L1, this is L2, and this is L3. So what is the question? I'm not able to understand.
No, the loop must be within the input and output because it's a transfer function, no?
No loop. Okay, so this node, every node is a variable. Every node is a signal. This node is a signal.
Yes, but it is
So,
coming from other line, not from
so what?
between the input and output.
So this for this signal. Okay, wait. Can we go here? So if you see G2, G2 is also a transfer function. It's not between input and output. You can see input is for G2, this is input, and for G3, this is input.
But it is
So
in
it's not
between.
coming direct.
But it is in between CS and RS, output and
Okay,
input.
it's actually okay. You're getting confused that it's not in between. So
Yes.
if you make a block diagram from this, then wait. So you are saying your question is it should be between this, but how can you say it's not in between? Because this is a they're again coming back to this point B, and B is in between A and C. They're somehow linked to B. You see that they're coming back to B. So in general, they'll be coming to B, but they're not visible. They're not directly
Okay.
visible, but they are linked.
Okay. 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 I see that.
Right? Maybe it will be more clear in the other question. The other question is, so we have to find. This is also in your assignment. Such questions are also in your assignment. So we are given this equations y2 y this sorry, these are the nodes y1, y2, y3, and y4, and we are given equations, and from the equations we have to draw the signal flow graph. Correct? So there is one question uh, of similar type in your assignment. So, but what's the hint here? The hint is y1 is the input, y4 is the output. Right? So let's assume this is y1. So this will be input, and this is y4. This will be the output. So again, I'm just recalling it. The node, actually, I have not revised what is node or what are those different terminologies for signal flow graphs. I assumed you know them from the lectures, but again, a node is a signal. Right? This node represents a signal, right? Wherever those G of S, E of S, or R of S, they are represented here with the help of nodes, right? So wherever I will represent a node, you have to be assume it is a signal. It's a signal variable, and this value of this node variable, for example, here this y2 or y3, these are all nodes, y1, y2, y3. If I have to find the value of y1, I have to see all the incoming signals to that node. I have to see all the incoming signals to that node, and I don't care about the excluding signals. So in order for me to find the value of a node variable, I have to only see the incoming signals to that node and don't care about the outgoing signals. For example, so we have this equation number one. We have this equation number one, which is y2 is equal to G1 over Y1 plus G3 over Y3. We know the variables, node variables are Y1, Y2, Y3, and Y4. And here I have Y2. So let's assume this is my Y2 bit. So let's assume this is my Y2. Now I told you that the value of this node variable is given by summing all the incoming signals that are coming to this node. So if I'm writing the value of y2, I'm considering all the signals that are coming to this node. I know y1 is the input node. So here, if it is y1, then I know it should be like this. It should be y1, it should be like this. y2 is equal to y1 g1, because incoming, as of now, incoming this g2. Then again, we have the other term is g3 y3. Here we have y3 somewhere here and somewhere here y4, right? So then so again, I from y1 to y2 I went straight, and let's assume here we have y3. Now I'm again saying this is coming back, so it's from y3 it's coming to y2, and with the gain of g3, so it will be now y3 g3, like this, right? So here somehow we will have y4, right? Now if you see, it will be more clear. If we see equation number two, is y3 is equal to g4 y1 plus g2 y2 plus g5 y3. Again, now the node under consideration is y3. So again, it's coming. So here it will be y2, and here it will be y1. Here it will be y4. So from y1, we are getting g4. So it's g4, correct? Then what is from y2? It's y2 to g3. It's as g2. From y2 to y3, it's coming with a gain of g2. Now another thing is, from y3 to y3, it's coming with a gain of g5. So I can write it like this. From y3 to y3, it's coming with a gain of g5, right? Similarly, if we have any other, what's the other equation? y4, g6 y2 plus g7 y3. So y1, y2, y3, y4. The node under consideration is y4. So from y4 to y2, we have g6, correct? And from y3 to y4, we have g7, right? So this is y2, this is y3, this is y1. So now if we compare this all, this is y1, y2, y3, y1, y2, y3, and y4, y1, y2, y3, and y4. If we compare this whole, what we will get, we'll get something like this. y1, y2, y3, and y4. From the first, we had y1 to y2 and y3 to y2. So this is G1, this is G3, this is G2, this is G7, Y4, Y3, Y2, Y1. This is G5. This is G6. And from Y1 to Y3, Y1 to Y3, I have G4. So this is the overall signal flow graph that we can draw from the equation. So if you are given equations, so consider this fact that the value of the node variable is given by summing up all the incoming signals to that node, and that's how we are writing the value of that particular node variable. And we don't care about the outgoing nodes signals. Then by combining, we should be able to recollect the whole signal flow graph. So there is one question in your assignment that uh, like that has this type of question. So we haven't covered like much content today. So quickly, we will uh, cover this time domain analysis. So I hope uh, you have gone through the lectures. So in that case, in time domain analysis, what we do, we observe the output of a system as a function of time by applying different inputs. So step input, ramp input, parabola input. Why do we apply these inputs? There is a whole story, and you have learned that. But here we're only interested in solving questions. So there are whenever we give an input to a system and the output CT, it is uh, actually transient value. It consists of this output of a this system. It consists of a transient value and a steady state value, steady state term. So this both are very, very important. So transient, it lasts for a very, very short duration of time, and then when our output it settles down, we call that as steady state. So you have studied both the transient response as well as the steady state response. There is a term very, very important in control systems, which is called as the steady state error. That is, when my response has settled, is has it perfectly tracked the reference input? So, or is there any error as t tends to infinity? So that is called as steady state error. And we will be solving problems on steady state error. You have some problems in the assignment which talk about that. And similarly, in the transient case, how our system is behaving, is it overdamped, underdamped, critically damped? So again, a whole different story. But before we start, so you should be able to know what is a type of a system. So you know the type of a system is, so you take this loop transfer function g of s h of s, if it is coming like this, k of 1 plus dz of s divided by s raised to the power p 1 plus dp into s. So this gives the poles at origin. So the number of poles at the origin of a loop transfer function, that gives me the type of the system, right? So if there are no poles, then it's type 0 at the origin. If there are one pole, type 1, two poles, type 2. You rarely have a type 3 system in your undergrad syllabus. So the poles at origin of a loop transfer function is called the type of a, gives me the type of the system. Similarly, order, there is another term, order of the system. So then if you take the closed loop transfer function, so I told you what is closed loop transfer function in the beginning, and the highest power of the denominator, the highest power of denominator in this CLTF is called the order of the system. For example, if the denominator is like this, s square plus 10s plus 3, then it is a second order system. We'll also learn these second order systems today quickly. So now there is this steady state error. So there is no time. Otherwise, I would have definitely derived the condition for the steady state error. But here I will directly write. So steady state error, normally it's denoted by ESS of S, or in time domain, because we are learning the time domain analysis, it is E of infinity, and it's given by limiting s tends to 0, s rs over 1 plus limiting s tends to 0, g of s, h of s. Correct? So there is a full derivation of this thing. We don't have time, so I'm not going into the detail of that. So just remember this steady state error, steady state error. It is the error as t tends to infinity. It's given by limiting s tends to 0. It comes from the final value theorem. We have learned that as well. S into rs divided by 1 plus s tends to 0 g of s hs. Now there is this important table which is very important. If we remember it, it comes very handy in solving problems. So if we have a type 0 system and we give a step input, AUT. A can be anything, unit or 2UT, 3UT, whatever. So in that case, we will get this steady state error. If it is a type 0 system and we give unit step, then we will get the steady state error as A divided by 1 plus KP, where this KP is called positional error constant, and which is given by limiting s tends to 0, g of s, h of s. Similarly, if I have type 1 system and I'm giving a ramp input, then and only I will get finite steady state error, the value of which is given by A over KV. And if I have type 2 system and I give parabolic input, then and only I can get finite steady state error, the value of which is given by A over KA. So this KA, KV, and KP, they are the positional velocity and acceleration error constants given by this. KP is limiting s tends to 0, g of s, h of s. KV is limiting s tends to 0, s into g of s, h of s. Similarly, KFA is limiting s tends to 0, s square, g of s, h of s. Now consider this question. Uh, let's try to solve this question. So we are given a block diagram of unity feedback. So there is this unity feedback means 1. There is no h, so it's h is equal to 1. The steady state error for the unit step is given by. So we know the steady state error. The steady state error for unit step input is given by A divided by 1 plus KP. From this formula, for a step input, uh, uh, we also have to check first the type of the system. So again, the type will be very simple. If we solve this system a bit, what will we get? What is GS here? GS is 3 divided by s plus 15 into 15 divided by s plus 1. This is g of s. What is h of s? H of s is 1, right? So I know. So this is a type 1 this is a type 0 system, because we need to check g of s, h of s, and there is no pole at the origin. So it's a type 0 system. Now we know that it's a it's a unit step. So my A here, so AUT, A is equal to 1. It's a unit step. Now I know my steady state error for a unit step, it is given by 1 plus Kp, and Kp is given by limiting s tends to 0, g of s, h of s, which is equal to limiting s tends to 0, 3 into 15, s plus 15 into s plus 1, which is equal to 45 over 15, which is equal to 3. So Kp is equal to 3. Our steady state error is equal to 1 divided by 1 plus 3, which is equal to 0.25, right? So this is equal to, this is the steady state error for a unit step input. So now you can see how handy this table comes. So if we directly remember this table for a type 0 system, this for unit step, we only have finite steady state error for type 0 system. Similarly, we only have finite steady state error in case of a type 1 system for a ramp input, and similarly for parabolic type 2 system. Now consider this question. The question is, a ramp input is applied to a unity feedback system, which results in 5% of steady state error. So we are given steady state error is given as 0.05, 5%. And what is the type, number, and gain of the system, right? So again, I told you the steady state error for a ramp input, it is finite. So if the steady state error is finite, you can quickly see from this table, if it is finite, there's no zero, no infinity, it's a ramp input, then it should be type 1 system. So from this, we can write it's a type 1 system, right? So it's the type 1 system, and the transfer function of type 1 system is given by, it's a general transfer function plus 1, right? So, and it's again, it's a unity feedback. So h is 1, then we know the steady state error. The steady state error is 1 over kV, and kV is limiting s tends to 0, s into gs, g of s into h of s. It's a unity feedback, so it will be limiting s tends to 0, s into k divided by s into s tau plus 1, s and s goes. And by putting on the values, we get this is 0, this is k over 1, so we got kv is equal to k, and it means my steady state error is equal to 1 over k. But I'm also given my steady state error is 0.05. It implies my k is 20. Correct? 1 over 0.05, and that's 20. Quickly, let's solve one more question. Or I'll come this question later on because I have to see look for, so yeah, second order system. You should be able to solve some questions like that, but second order system. So I told you the order of the degree of the denominator in the closed loop transfer function of a system. It gives me the order of the system. So clearly here the order is 2. So it's a second order system. So second order systems are very, very important in control systems. So this is the transfer function, a closed loop transfer function of a second order system. It's a general way. So it's very, very important. Here, this omega n, it is the natural frequency. So this omega n, this is the natural frequency of the system. Similarly, the zeta is called damping ratio. If this zeta is greater than 1, then our system is called as overdamped system. So what does overdamped mean? It means damping is more than required. Similarly, if my zeta is less than 1, it's called underdamped system. Again, it means the damping is less than what is required. Similarly, if this is equal to 1, then my system is critically damped. It means damping is exactly what is required. And if my zeta is 0, it means my system is undamped. So sometimes you have to identify whether you are given a second order transfer function and you have to identify whether the system is uh, like overdamped, underdamped, or undamped, right? So you can, one way is you can look at the value of zeta. You can solve that a bit because this is a general form, s square plus 2 zeta omega and s plus omega n square. So you have to convert that second order system into the standard form, and then you have to find the values. But again, there are some other ways also to check whether the system is underdamped, it is an overdamped, or it's a critically damped. For example, if it is an underdamped system, then my poles, I have two poles because S is square, I will have two poles. My two poles, they will be complex conjugate of each other if my system is underdamped system. Similarly, if I have a critically damped system, my poles will be real, but they will be equal. If I have an overdamped system, I will be having real and unequal roots. Similarly, if I have undamped system, then my poles will lie on the imaginary axis. So you will go through these characteristics. Similarly, then whenever we study a second order system in time domain, we make sure that uh, uh, like we study some properties like rise time. So for example, in case of an underdamped system, what is the time it takes to reach the steady state value, like the first time it reaches the steady state value. Then when it reaches 50% of the steady state value, that's called as the delay time. Similarly, there are many other things, peak overshoot. For example, quickly, I'll draw the response of this is time and this is CT, and let's assume this is steady state, this is 1, let's assume, and I have an underdamped system, so it will be something like this. So if this is 1, this is the reference, this is my steady state value. So the first time my this this response, it reached the steady state, it's called as rise time. Let's assume it's 0.5 here. The time it took to reach to 0.5 is called delay time. Similarly, it should have settled here, but it's going up. So this is undesired, this is not desired, and this is called peak overshoot, right? So peak overshoot also has formulas. For example, it's given in percentage maximum peak overshoot. The formula is e raised to the power minus zeta pi over 1 minus zeta square, right? And into 100%. So this is how you calculate peak overshoot, etc. So let's see whether I have some questions on this system. So the block diagram of a closed loop system is given. The value of K and P such that the system has a damping ratio of 0.7 and an undamped natural frequency of 5 radians per second respectively. So we have to find the value of uh, P and K from this system. So clearly, we can see the system is in feedback, right? So it's a negative feedback. So we can write the overall transfer function quickly because we have solved many problems. We can quickly write k divided by s into s plus 2 divided by 1 plus k divided by s into s plus 2 into 1 plus sp. So it's nothing g divided by 1 plus gh, right? And after we solve it, we get the value as k divided by s square plus 2 plus kp. Sorry, it's k into p into s plus k, right? So now we can compare. We know the general equation of a second order system is s square plus 2 zeta omega ns plus omega n square. Here it's also omega n square. So omega n square is equal to k. So I am given uh, omega n is given. So k is omega n square. So it implies my k is 5 square, which is equal to 25, which is equal to 25, right? And also I know 2 zeta omega n is given by 2 zeta omega n is given by 2 plus kp. And then after we solve, we get 2 plus kp is equal to 7, right? By putting in the values, you are given this damping ratio is 0.7. So I just put the values 5. It will be 0.7 into 2 into 5. That will be 7, and then k into p will be. It will come out to be 7 minus 2 is 5. I know k is 25. What is the value of p? It implies p is 5 over 25, which is equal to 0.2. Right. So one last question. It's from your assignment. Then we will conclude. I'm sorry we couldn't solve much problems today because they were longer questions of block diagram reductions and signal flow graphs. But yeah, let's solve this question. Try to solve this question. Then we will end up today's lecture. So consider the system shown below. Determine the value of k such that the damping ratio is 0.5. And also we have to obtain the settling time. And settling time has a formula. Settling time has two formulas. One is for 2% tolerance band and other is for 5% tolerance band. That comes later. But first, we have to determine the value of k such that the damping ratio is 0.5. So what you can do, this clears all your doubts regarding block diagram reduction as well. So first, what we'll do, this is in feedback. So this is in feedback. Let's assume the value of this comes out to be G1. So it will be 16 divided by S plus 0.8 divided by 1 plus 16 divided by S plus 0.8 into K. So that will be G1. Then that G1 is in cascade with 1 over S, right? That G1 into 1 over S is fed back with unity. So it's then with unity feedback, right? So I hope and this is clear. So G1 comes out to be 16 divided by S plus 0.8 plus 16K. This is G1. And then when we feed that back, we calculate the overall transfer function as C over S divided by R over S. It's coming out to be 16 over S square plus 0.8 plus 16K into S plus 16. Right. So now we got the general form. We know the general form is S square plus 2 zeta omega ns plus omega n square, omega n square. So omega n square is 16. What is omega n? Omega n is 4. We got the value of omega n. Similarly, we know that 2 zeta omega n is equal to 0.8 plus 16. K, by solving, we get K as 2 into 0.5 into 4 minus 0.8 over 16, which is equal to 3.2 over 16, which is equal to 0.2. Correct. So I got the value of k as 0.2. So fine. Now in the question I was asked about the settling time for the 2% tolerance band. So settling time for the 2% tolerance band is given by 4 over zeta and omega n, which is equal to 4 divided by zeta is, what is zeta? Zeta and omega n. So that is 2, and which is coming out to be 2. That's the settling time is 2 seconds. Correct. So the main crux of this question was, first you have to identify the feedback and reduce this question, reduce this diagram and get the transfer function. Then that transfer function you have to sort in the standard way, that is for the second order system, 2 zeta omega n s, then compare with the standard equations, get the values, and then get the value for settling time. So there are some questions which I have skipped. Just check. Yeah, there are 2 questions which I have skipped. So if any one of you is interested, we can solve them as well, or I can give hints. I can give hints at least. So first, I'll give hint to this question. This is a very important question. This is from your assignment as well. So there are 2 ways we can solve this question, right? So see, it's given that we are applying the ramp input. So given that we are applying ramp input, so it means we are applying a ramp input, and it is decided that the steady state error is this. The complete range of values for error to be within specified limits for the unity feedback. So we are given g of s, and h of s we are given as 1. And it's also given that we are applying a ramp signal. So we know for the ramp input, this ESS is given by A divided by KV, and then KV is limiting S tends to 0, S into G of S, H of S, right? So then we can find this value for KV by putting out the values. We'll get something. Then we will put that here ESS is A over KV, but ESS is given, it is less than 0.005. So if it is less than 0.005, and again, you have to make sure that this A has a value here. A is 0.1T. If you remember this table, see, A, T, U, T is ramp input. So A here is 0.1. So in the question given, AT is 0.1. So then you will get some value. So do you want me to solve it, or you can try on your own? Number one, this is the first approach. The other approach is very simple. So you know what is this? It is limiting S tends to 0, S R S divided by 1 plus G of S, H of S, right? So again, the same thing, same story. Put the values of R of S. You know what is R of S? R of S is 0.1 over S square. Then put the value of GS, HS, simplify, you'll get a condition. Then from that condition, you'll be easily able to find the range of K. And for this, I'll give you answer. This is the correct answer. You just try it. So there are 2 ways. If you try this way, then you don't care about the value of A, because then you are solving from scratch. But if you are solving it from the table, make sure you apply this value of A. And in any case, if you have any doubt, I'm giving my number, so you can ask me on this number. So you can WhatsApp me your queries, and I will be. I'll try to answer. I try to reply back, or if you have any doubt, we can also discuss. Right. So this was question number one, and the other question was this. So this is when subjected to a unit step input, the closed loop system will have a steady state error, right? So this unit step will have a steady state error of. So what we have to do here, we have to simplify it. We have to simplify it again. Uh, we are given it is subjected to unit step. So we know that ut. So r of t is ut on r of s. This is 1 over s. We know that. We know what's the value of r of s, and we know we can calculate this. This is gain. This is summer block. Then will be in cascade. You'll get something. Then from that you'll get the value of y. You can apply final value theorem and get y infinity. So that is what is required. You know the response should be this is the input u steady state, and like how your y is responding. If your y is also settling at 1, your input is also 1, it means there is no steady state error, right? And in this case you will get steady state error is equal to 0. So there are many ways to interpret it, and I'm leaving it as a homework. And again, if you have any question, uh, you can contact me. Just try to simplify it a bit by using block diagram reduction, then find ys, then find y of t, either by taking inverse Laplace or by using initial value theorem, and then see what you will get. And you have given other things as well, other table as well. So again, if you have any doubt, you can contact me here. So I'm erasing it now. So yeah, thank you very much for joining. So I'm just stopping the recording. So that was it. Thank you very much for today's session.
Thank you, sir.